This video is for correlation, and a side note, I am using an equation that's different from the textbook, so I would focus on the notes for this chapter. And I'm also adding another type of correlation that's not covered by your text. So we're going to do two types of correlation for two different kinds of data. But first, before we calculate anything, we are going to talk about scatter plots. So a scatter plot is just, your regular graph that has a y and x-axis, and then the dots are the data points from the x-y pairs. So if there is a relationship, then you would be able to draw a line. For example, here, as the x increases, as the cups of coffee consumed increase, then the nervousness scores also get high. You could have a relationship that is negative, and then you would have the data points in the line going downwards from the left to the right going down. And that would be a different type of relationship, different type of variables. A linear relationship is when we are able to draw this line, basically. We're going to have other scatter plots when it's not as easy to draw an actual linear relationship. The stronger the linear relationship, the higher the value of the correlation coefficient, essentially. So let's go down here to this next example. A researcher was just to see if there is a relationship between age, it should be age, not ages, and net worth for the wealthiest people in America. So would you expect the relationship to be linear? Meaning, let me try it here. Meaning the older, let me show you the scatter plot here. The older people are, age, wealth on, okay, that you cannot read that, wealth on this side. The older people get, the more wealth they have, so that's one type of linear relationship. Or would you expect to have less wealth? Like some people get older, they cannot work as much. What type of relationship would you see? Look, I actually paused the video and think about it a little bit. So let me show you the scatter plot here. I could force a linear relationship here. I could force a linear relationship here. I could even force a linear relationship here. The truth is, for this type of relationship, it's actually a curvilinear relationship. The best way to describe it is a nonlinear relationship or curvilinear. Another way I've seen it called is concave up. So whenever we have a data set that is not necessarily linear data, then when we try to calculate the correlation for that, because the correlation is a measure of linearity, we're going to have a very low correlation. And it could be a very low negative correlation or a very low positive correlation. It really, because it's going to try to force the lines here, but it's never actually going to be strong enough to find a correlation, just because the data doesn't support it. So that's what's going to happen. Whenever we try to find the strength of the relationship through the correlation for a curvilinear relationship with like this one, or a curvilinear relationship like this one here, it's just going to be a low value. And it doesn't mean that we cannot do anything with this type of data. Of course we can. It just means that we cannot use correlation to model this data. It means that we have to learn other methods, and they are called non-parallel parametric. Oops, methods. And that's a different class. Not this one. We mostly focus on data that is linear. Or if it's not linear, we just say, well, this data, it's not good for correlation. Things you need to know about the correlation coefficient. The range can be -1 to +1. So the closer it is to 1, that means that the relationship is strong, but it's also positive. The closer it is to -1, that means the relationship is strong as well, but it's negative. The correlation coefficient could also be close to 0. That doesn't mean that there's no relationship. It just means that the relationship is weak. So the correlation coefficient is a descriptive statistic. What does that tell us? It essentially tells us that we are calculating it from the sample. So I'm going to put a little note here on the notation. The Greek letter rho represents the population correlation, meaning is a parameter. And then just the generic, that's actually the right word, the Roman letter R represents the sample correlation. And that is a statistic. And it's a descriptive statistic, essentially. What the correlation coefficient is doing is that it's simultaneously modeling the variance for all of the pairs between X and Y. And we kind of tend to use the words interchangeably, like correlation and relationship. It is kind of used interchangeably. So, one thing you need to remember from this section, and you're going to have some questions about it later in Canvas, is that correlation does not imply causation. So you can have a correlation, and even more if your data set is big, but that doesn't mean that there's a relationship. It's just their numbers. They're going to correlate anyway. So just because you have a correlation, that doesn't mean one variable causes the other. It doesn't mean that X causes Y. So let's talk about this scatter plots. So for example, the very first one, I have a correlation of 0.50. That's like in the middle of a positive linear relationship. And you can see the dots are a little bit spread out, but not crazy. Then I have a correlation of 0.90, and you can see the line forming more clearly here. And if we keep going to a correlation of +1, that is a perfect positive linear relationship. Let's keep going. I'm going to change my color here. So over here I have a scatter plot, and that is a negative relationship. My correlation is -0.5. That doesn't mean that there's no relationship. It just means that whatever relationship X and Y have, it is in the negative direction. I have the same type of data. I'm going to skip all the way to F. This is a perfect negative, strong relationship between X and Y. And you can see that when you draw the line here, it's going down. This table is going to help us describe our correlation. After we calculate it, we're going to come back to this, and then let's say it's between -0.9 and -0.7. So we can call the correlation strong, and it's obviously negative, so that's the direction. Over here we have the positive values. So I would put a pin on this because it can definitely help you when you're writing up your APA description of the correlation. Another thing that you should know is that these guidelines are from a textbook. It really matters the context that you're in. There's going to be areas where having a correlation of 0.2 means something. It's important. And there's going to be areas where no, it's really not. So it's context dependent, basically. So now let's talk about the formula. We are going to be using the Pearson correlation coefficient formula. It's important that you know because we have more than one formula for correlation. And the reason we use the Pearson one is because it's for continuous data. So the difference between the, I don't know, 3 or 4 correlation formulas that there are is the type of data that you have. So this one looks ugly, I know, but it's what we have. It is definitely used for continuous data. So notice that the symbol is R. Over here we have N, which is going to be the number of pairs. And then we have sum of X, Y. So first we multiply X times Y, and then we sum them. Sum. This is just sum of X. This is going to be sum of Y. Then I have sum of X squared. So first square the X, then sum. Same for the Y. You square the Y. Let's try to pass this as a Y. Then sum. I think that's all you need to know. There is an implied multiplication here. That's another thing that causes people trouble. And another thing that I see students forget a lot, it's the square root. I don't know why, but they do. They forget the square root. It's there. Don't forget it. Remember that the X is going to represent the independent variable. Another name for it is predictor. The Y is going to be the dependent variable, and it's what we call the response variable. So let's do our first example. So our first example is absences and final grades. So X is going to be our IB. Y is grades, and it's going to be our DB. So absences is here, X, Y. And you can see there's a relationship in the data set just by looking at the scatter plot. You can see it's definitely going down. So as the student has more absences, the grade actually goes down. Okay, that makes sense to me. So we're going to fill out this table first, and then we are going to actually calculate the correlation. This table is very tedious, but we have to do it. So the N is the number of pairs. So 1, 2, 3, 4, 5, 6, and 7. Here we're going to sum the X's. I know that's the X's because I put it on the table. And that's going to be 57. Let's change colors. I'm going to color code it the first time, and then I will not because it just takes a lot of time. 57. Then let's use green. The Y, the sum of the Y's, we add this column. That is going to be 511. Let's use a nice blue over here. Now I need to multiply the X and the Y, and then after I multiply them, I'm going to add them. So here I'm going to multiply 6 times 82, and that is going to be 492. Here's going to be 2 times 86, and that is going to be 172. So you got the gist of it. So it's going to be 645. This is going to be 666, 696 as well, 450, and 624. Then we add this whole column, and that is 3,742. 3,745 actually, sorry. Purple. Now I'm going to square the X, and then after I square them, I'm going to add the column. So here it would be 6 square, 36. Here would be 2 square, and that is 4, 225, 81, 144, 25, 64. When I add the column, I get 579. Nice. I need another color. Let's use pink. No, I already used pink. This other pink. So now I need to square the y from this column. So it would be 82 squared. And that is 6,724. Then 7,396. 1,849. 5,476. 3,364. 81,000. 81,000. 60. 84. And then I add this column, and that's going to be the sum of the y squares, and it's actually a really large number. There it is. That's the answer. So now that I'm done with the table, I'm actually going to move it all the way like this, because I do need to look at those numbers. I'm actually going to try to find the correlation. So the number of pairs was 7. So 7 times the sum of x times y, which was blue, minus the sum of x, which was pink. I don't know why the keyword shows up all the time. I swear. I tried to stop it, but I can't. Times the sum of y, which is 511. All of this is going to be divided by the giant square root bracket, 7 times the sum of the x's already square. So that's actually this one over here in purple. Again, I'm going to color code it the first time, but I can't be color coding it all the time. Minus the sum of x, which is 57. But this 57, we have to square it. And then I close the bracket, open bracket. So this yellow part is just this bracket, basically. I need the number of pairs again. 7. The sum of the y's square, which is the giant number. 38,993 minus the sum of the y's, and then that sum of y's, which is over here, 511, I am going to square. And then I close bracket, and my square root goes all the way there. There we go. Oops. So what I recommend is that you calculate each bracket individually, and then you calculate the top of that equation. So let me go to Google and hope for the best. So I'm going to calculate the top first. It would be 7 times 3,745 parentheses minus parentheses 57 times 511. Cross your fingers. That is exactly what I wanted. So wrong place. R is negative 2912. So what I'm going to do is I'm going to calculate the first bracket just to show you how it's done. 7 times 579 minus 57, but this 57 I need to square. 104 and then the other bracket is going to be a bigger number, 11,830. But here, don't forget the square root. and then you can go ahead and multiply those two. But it's usually going to be a very large number, so I tend not to, I just do it within the calculator and write it out. So 804 times 11,830 is this really big number. So what I do is I just do square root, and any calculator has this answer, and answer is actually that number. And I like putting answer because I don't have to type in the numbers and then I'm risking typing in the wrong number, which I do often. So that's actually the denominator for our wonderful correlation. 84.04 negative 2912. So this is after square root. And then when I calculate the correlation, I get negative 0.944. So the next thing we have to do is talk about the direction. It is a negative correlation. And we would go to that table. So our correlation is negative 0.944. So I would say it's very strong and negative, but I already know that. Very strong negative correlation. There you go. Let's go to the next problem. It's the wealth and age data. So if we tried to fit a linear model in this data, in this scatter plot, we could go here, we could go here, we could be here. Maybe I could try to go in here as well. So what this tells you is that a linear model is not probably the best way to go with. So if you actually try to do a curvilinear one, it might actually represent the data better. But the correlation is a linear measure, so what I expect here is to see a low correlation, something that's close to 0. So here I already fill out the table, but I do have to find the sums of the table. So remember, n is the number of pairs, and that is 8. I like this color. I'm gonna use pink. The sum of the x's is going to be a big fat 519. The sum of the y's is going to be 208. The sum of x times y, it's going to be huge, 13,357.5. The sum of the x's square is going to be 34,227, and the sum of the y's is going to be 6,491.5. Okay, now that we have the sums, let's actually calculate the correlation. So it's going to be 8 multiplied by the sum of x times y, which is 13,357.5, minus the sum of x, which is 519, this one, times the sum of y, 208. Then I'm going to have giant square root, and give myself a lot of space, bracket, so 8 times the sum of the x's squared, so that's always going to be the larger of the two sum of x's, just in case they're confused, minus the sum of x, which is 519, square, close bracket, open bracket, 8 times 6,491.5 minus the sum of y, 208. But this sum of y we have to square. Okay, so when I calculate the top of the equation is also negative, like it was in the previous problem. It's not always going to be negative. It just happens that the two problems we picked have a negative correlation. My giant square root. When I calculate this part of the bracket, of the denominator, I'm sorry, I got 4,455. That's the first bracket. Second bracket is 8,668. Let me just color code this one so you know they're the same. After I multiply this 2 and take the square root, I get this. So again, after I multiplied and took the square root is 6,214.17. And the correlation is going to be negative 176.176. Okay, so it's negative. Now I just need that word to classify the dimension of it. So 0.176, negative 0.176 is between 0 and negative 0.2, and we can call it negligible and negative. Negative correlation. And the reason why it's negligible is because of the relationship in the data. Remember, it's curvilinear really, and we're trying to fit a procedure that is used for linear data. Talk about range restriction. So this is when the lowest and high scores on both of the independent and dependent variable are limited. So that makes our correlation coefficient less accurate, and very likely it's going to be smaller than what we would expect if we had not restricted the range. This is something that could happen when you do survey research because people volunteer information, and you cannot really force people to be part of your study. You cannot force them to give you certain information. They can always decline. So it's very likely that if you ask them to give you the scores, it might be incomplete data. So let's look at the whole data set here. I have SAT total at the x-axis, my independent variable, and I have freshman GPA as my dependent variable. I definitely see a linear relationship here if I wanted to fit my data. And I can see that it's positive. What if I only take this group of people? What if I accidentally only survey people with very high SAT scores and very high GPA? Look at that relationship. Would it be linear? Would you be able to fit a line here? Or maybe could you fit a line here? So that would be a positive correlation. The previous one would be negative. So it would be more difficult to find the correlation here, and it would likely be a low correlation. So I made up some data in Jamovi to basically do the same thing. I have a variable that's SAT total, and then I have a variable that's GPA. Let's just do a scatter plot for the whole thing. That looks positively linear, and Jamovi has this option where you can actually put a line in there. Yeah, positively correlated. What happens, I kind of ordered my data on purpose so I could do this. What happens if I take all of the scores that are greater than 1,000 and then I put them over here in two other variables? Let's do the correlation for this. I'm sorry, let's do the scatter plot for this one. Scatter plot. SAT total and GPA. And let's put the little line, sorry. That does not look good. It's having trouble fitting that line, and it put it as a negative relationship. Let's actually just do the scores, the big scores, with just this other variable that I put the age on, and the GPA. So those are the high scores, and it's again a linear positive relationship. Now let's do all of the correlations to see what happens there. To do correlation, I do regression, correlation matrix. Let me move the data back so we can start from the big data set and then move to the small data set. So regression, correlation, I'm going to drag this too. The correlation is 0.68, definitely positive. I wouldn't go and call it strong, but it's not bad. It's not 0.5. Let me split the data again. And that's fine. So if I only do the correlation for the two variables with the range from, it looks like 800, 700 maybe, and the highs is 999. That correlation is negative and it's very small. And we kind of saw it in the scatter plot as well. Now let's do a correlation for the high-end scores. Yeah, it's positive and it's even higher than when we have the whole data set. So that's interesting. What I'm trying to say here is that the range that you have in your data set, it's gonna matter. It's gonna have an impact on the correlation that you have. In case you're wondering, if you ever want to find out the range, you can just do descriptives. You can ask for the range and then the minimum and maximum. Let's do for the small data set, small values data set. Yeah, so that my minimum is 700, the maximum is what I said it was, and this is my minimum GPA, my maximum GPA. Now let's go back to our notes so we can go over another more detail about the correlation. It matters if you have outliers. Outliers will make your correlation stronger. What is an outlier? It's an extremely small and extremely large value in your data set. So here's my data set, and this is my outlier. If I calculate the correlation with that outlier, it's going to be this number, which is insane. That's a pretty big correlation for just randomness. If I take this out and I just calculate the correlation for this part of the data set, that correlation would be 0. R equals 0. Oops, that's not a 0. So let's go to Jamovi and let's see if this is going to happen with the data that I made up. So for this, I'm going to use X outlier example, Y outlier example. I'm going to start with the scatter plot because I like scatter plots. Analysis, scatter plot, outlier, X outlier into the X, Y outlier into that. So you can see it's just the same dots. Let's try to fit a line here. Okay, that's not helpful. Now let's add an outlier to our data. Let's say, I don't know, 30 and 23. So let's see what happens to the scatter plot. Ooh, yeah. And you can see it's trying to fit the line as well. And it's saying it's pretty positive. So let me remove this again. Let's try to do the correlation for that data. X, Y. The correlation is 0. Now let me add 30 and 23, my outlier, and see what happens to the correlation. Oh my God, that is ridiculous. So again, an outlier is going to influence whether when you do a correlation. So always search for outliers when you're calculating your correlation. Okay, so let's talk about the Spearman rank order correlation coefficient. That's hard to say. When we were doing the previous type of correlation, in case you didn't notice, we were using continuous data. For the Spearman rank is in the name, correct? The data has to be order. They have to be ranked. We're dealing with ordinal data. So it's a type of non-parametric test. And my understanding is that non-parametric statistics are very popular in the social sciences because researchers tend to use Likert type of data where the participants rank their choices basically. The good news is that the formula is pretty easy compared to what we just did. It is so much easier to use. What you need to know. N is going to be the number of pairs, and we kind of knew that already. And then D is going to be the difference between the X and the Y. One thing you need to know is that I'm already giving you the data ranked. So for example, we're going to find the correlation assigned by researchers. So researchers saw many children and then they ranked them based on a certain behavior. And there was 2 researchers, observer A and observer 2. So each person has their own ranking, but it's the same person, the same participant over here. So the same participant got ranked twice by 2 different people. What we're trying to see is how those rankings correlate with each other. So here I already ranked the data for you. In real life, if you conducted a study and you wanted to find the correlation of ranked data, you would have to go ahead and create this table where you put the rankings in order. And another thing is that you would have to solve ties. Like if you had a 2 here and a 2 here, you would have to solve that tie. And the way of doing it is kind of complicated. That's why I'm working around it. But be aware, in practice, it's actually harder than the Pearson correlation. For us, because we're still learning how to calculate things by hand, it's actually faster. Okay, so I have my participants. My N is going to be 9. Then I have the observer A rankings. I don't need to add those. Then I have my observer B rankings, which is going to be the Y. Again, I don't have to add those. What I do have to do is find the difference. So D is going to be X minus Y. That's what D is going to be. So 4 minus 3 is going to be 1. Negative 1, 1. This is very convenient math. Negative 2, 1. Negative 1, 1, 2. Sorry, negative 2. I still don't need to add them. What I have to do next is that I have to square the D. So D squared would be 1 squared. Okay, I don't really have to do that, but I'm going to do it anyway. Negative 1 squared. Whenever you square a negative number, it becomes positive. And this is where I see the most mistakes in this piece. I don't know how else to mark it like this. When you square a negative number, it becomes positive. Just tattoo it in your brain because it's going to happen to you and you're going to get things wrong. So don't let that be you. 4, 4, 1. I'm in trouble with the lines here. It's kind of confusing. 4. And then I'm just going to add this column. When I add that is 18. And that is going to give me the sum of D. If we look at our formula, it's actually this piece here, the sum of these squares. I already know what the N is, and I know it from here. It's 9, so this is going to be 9, and this is going to be 9 squared. That's it. That's all I need to do. So let me tell you another place where I see a lot of mistakes. So don't ever forget the one over here. Students just forget it all the time. I've done it when I'm teaching sometimes, but that's usually where the mistakes come from. So that 6 is always going to be there. It's just part of the equation, and then times 18 divided by 9. 9 squared minus 1. So it's going to be 1 minus 108 divided by 9 times 81 minus 1. So 1 minus 108 over 9 times 80. And then I get 1 minus 108 I have to move this a little bit. Minus 108 divided by 720. I just pause the video so I could give myself space. When I calculate this piece, finally, would be 1 minus 0.15, and when I do that subtraction, I get 0.850. So most of the time, students give me this answer, and I just know they forgot the 1. And they forget it pretty early, like they'll forget it in this step, and I just keep working. You don't have to do all of these steps. I just did it because I am teaching you this. I definitely need to see this piece and this piece. Okay, let's do another one. So again, we have skaters. It's the same skater that's being ranked by 2 different judges. I think they're judges, yeah. So here's the participant. My N would be 6. X is the judge, and then Y is the other judge. And I have the rankings here. Let's find a difference. So it would be 0, and then 0 again, 1, -3, just 1, and 1. Convenient. When I square is 0, 0, 1, 9, 1, and 1. When I add those, the sum of the differences square is going to be 12. Now I just need to find my correlation. So 1 minus, that's not a minus, 6 times 12 divided by 6 squared minus 1. 1 minus 72 divided by 6, 36 minus 1. Let me keep going down here. 1 minus 72, 210. Oh, minus looks ugly. Then I finally do this division. So it's 1 minus 0.343. And the answer is 0.660. So that is my correlation.